Good afternoon, everyone. Hang on, let me unmute. Good afternoon, everyone. My name is Franca Tamaris. I'm the Events Coordinator for the Melbourne Energy Institute. Welcome to our seminar today on green hydrogen as an alternative to natural gas. Before we begin, I'd like to acknowledge that today we're gathered on the lands of the Wurundjeri, Woiwurrung and Boonwurrung people who have been custodians of this land for thousands of years. We acknowledge and pay our respects to elders past and present. Thank you for joining us today for the 5th seminar, focusing on gas. We've had some interesting seminars which have been recorded and are available on our website. Some instructions for our online audience. If you have any questions, please enter them into the Q&A box as a chat function is disabled. We will have some time for Q&A at the end of this session, and we'll endeavour to get through as many as we can. I would like to introduce Professor Richard Sandberg, who will introduce our speaker to us.
All right, thank you, Franca, and a warm welcome from me as well. So I'm Richard Sandberg. I'm the new director of the Melbourne Energy Institute, and I'm also a professor in the Department of Mechanical Engineering. So I'd like to welcome you all to this seminar today, which I'm going to moderate. And it's my particular pleasure to introduce our speaker today, Michael Bielinski, who's head of projects Asia Pacific at Siemens Energy. Michael has over 35 years of experience in the local and international power generation and transmission industries. He initially worked in operational power plants and then moved to plant design, project management, and business management. He's worked on projects in Australia, England, Germany, and throughout the Asia Pacific. He holds a Bachelor of Engineering honours and a Bachelor of Science degree from the University of New South Wales and a Master of Engineering Science degree from the University of Newcastle. So thanks again for joining us. And again, it's my pleasure to introduce Michael, and over to you. We're looking forward to your talk.
Thanks very much, Rich. Good afternoon, everybody, here in person and online. So firstly, thank you very much to those who came in person. Okay, just some short introductory words. So today we're talking about green hydrogen as an alternate to natural gas. What I would propose to do is not to actually talk about the detail of technology of how we produce green hydrogen, and specifically not to look at green hydrogen as a silo. We think one of the problems with the energy transition debate is often people look at things in silos. Rather, what I'd like to look at is where green hydrogen can or must fit into the overall energy transition and why we think it will be important. Okay. I think also as an introductory comment, in the last 12 months, quite a lot of momentum has come out of the green hydrogen industry and projects that have been developed, particularly in Australia. Why is that? It's pretty clearly one thing, which is cost. So what we see is green hydrogen as an energy source is quite a lot more expensive than the natural competitor, which is natural gas. The question is, what does that look like, and how do we fix that over time? Okay. Now, in order to see where green hydrogen fits in this transition thing, what I would like to do is use as a framework a study that we started in 2019, so more than 5 years ago, pre-COVID, that time, a long time ago. And this study started out as actually as an internal strategy investigation. We wanted to see where would the energy markets go in the future, and we realized, of course, that predicting the future, even 5 years ahead, is really, really hard. We made one observation, though, which was that actually with this energy transition thing, we know exactly where we want to be in 2050. We want to be at net zero. So that's very unusual when you're predicting the future, right? Where you know exactly where you want to be. So what we did was we said, well, why don't we go to 2050, work out what we would have had to do to be at net zero using technologies we know about today, and then work backwards to the present to get and our main goal was to get a rough feel for the size of the numbers, the size of the challenge. Okay. And we hoped that in doing that process, we would learn some things. And as it turns out, we did. So what I would like to share with you is that process We did to get this view of what could the energy transition look like. And from that, we see where green hydrogen actually has a place to fit. So that's the sort of the rough overview of what we're going to do today. There we go. Okay, so we do this in 4 steps. So first thing we look at is quickly look at today's emissions and electricity generation in Australia today. We then do a first step, which is what we call the thought experiment. We say, what would it take to get to net zero in electricity generation? And in doing that, we develop a model and a way of analyzing and so on. And then we take that model, we take the big step, which is what happens if we take all of the fossil fuels out of the economy and just rely on renewable energy generation to get to net zero. And then we draw some conclusions. So 4 steps. Yeah. Okay, today's emissions and electricity generation. So you'll see this stack bar graph. This shows us in the dotted red box are the CO2 emissions from our economy today or in 2024. So electricity generation is still about 30%. Transport's roughly 20%. Stationary energy roughly 20%. Fugitives, which is mainly natural gas escaping either from when we dig coal out of the ground or when we extract natural gas out of the ground. And then industrial usage is about 6%. And we see on the right, their agriculture is about 15%. Land use consumes about 15% roughly. But we'll focus on the part in the red box. Yeah. And goal, of course, is to get that down to 0. Okay. If we look at the historical trend of CO2 emissions from the Australian economy, we actually see we're doing okay in reducing our emissions. Okay. In 2005, we were about 630 megatons per annum. We've progressively reduced till 2024, about 446. Target for 2030 is 360 megatons per annum. And of course, 2050, our target is still 0. Now, why have we reduced in that period of time? And we've reduced while we've significantly increased population. That's quite difficult to do. We've reduced partly because we've decarbonised. We've gone producing lots of electricity with wind and solar. We've also deindustrialised our economy to some degree. So those 2 things together have helped us reduce substantially. Okay. If we look at today's electricity generation mix compared to where we were, so you'll see in 1994, about 90% of our electricity was generated from fossil fuels. About 10% was renewable. If we move forward to 2024, we're at 38% is produced by renewables. Okay. So that's a very big change, particularly in the last 10 years. So as a country, I think we quite often just criticize things. We actually have done really, really well to significantly grow our renewable energy generation. Now, the federal government has a target that by 2030, we want to get to 82% renewable electricity generation. I think you conclude that's a pretty hard target to achieve. Okay. We only have another 5 years to get there. So it's going to be very, very ambitious to achieve that target or even get close to it, I think. But we've done well in the recent past. Okay, and then just reminding ourselves again of the electricity industry as it is today. This map shows you the transmission networks around Australia. Now, what's not really clear on this map is that each state is actually quite similar to the others. There is a main node of consumption, which is the capital city in that state. There are 1 or 2 nodes of fossil generation within a few hundred kilometers of that city, with strong transmission connections from the generation nodes to the city, and then relatively weak links to adjacent states. That's been the situation for 30 years. Okay. And where this becomes a problem for us as we go to more and more renewable generation is we want to build wind and solar generation, typically not in areas where there is existing transmission. And that means one of the things we have to do is build a lot more transmission. Is there likely to know? Okay, so that was a very quick run through where we are today and where we've been in the recent past. Last slide on today is in order to do this analysis into the future, we had a look at this, and in electricity generation, of course, there is the yearly cycle of seasons, but in particular, there's a daily cycle where we have historically more consumption during the day when people are awake and at work. We used to have evening and afternoon peaks. They've sort of flattened out in the last years. And we have, of course, the solar peak during the middle of the day. So we've created this graph, and I will focus on this for a few moments because we have several variants of this graph through the presentation. This graph shows a 24-hour period from midnight to midnight. The red line shows the electricity demand throughout the day, and the different colors show how we fill that demand today. So from the bottom, you have coal, both brown and black coal is the black part. The wind is green, and you can see on average throughout the year, wind is relatively consistent on a given day, not. The blue is hydro on average, grey is gas on average, the light yellow is distributed solar, and the dark yellow is utility solar. Okay, and that mix of different technologies is how we fill demand today or make demand today. Yeah. Okay, and we'll keep going. Okay, so now we get to our thought experiment, which is how do you by 2050 get to net zero in electricity generation? So if we can focus on the left-hand graph first. So this graph shows the period from 2020 to 2050. The yellow line shows population in Australia. So Australia is probably the only first world economy that is anticipating strong or any population growth. And we expect by 2050 that it will grow by about 50% from 2020 levels. And we know that with population growth grows energy consumption growth. During the same period, the black line shows the planned closure of coal-fired generation in Australia, down to zero by 2050. Okay, so we have to compensate for that if we are to generate all of our energy renewably, and we assume either with the existing hydro and then with more solar and wind. The right-hand graph then shows the falling away of gas generation, the falling away of coal generation, and the growth of renewables we would have to have.
Sorry, I'm just increasing the volume.
Oh, thank you.
Sorry, keep going.
Well, you do that.
Just make sure it's not muted. No.
Is that better? Is that a little bit louder in the room? I hope so. So the right-hand graph shows the green line is the growth in renewables we would have to both compensate for the closure of fossil capacity as well as any growth in demand due to population during that period. Okay, and that growth is simply the growth we need to provide the average day electricity consumption, the graph we saw earlier. So in this, we don't currently address 5 or 6 days of bad weather. We'll come to that later in the presentation. Yeah. And the mathematics behind this is really quite basic. This is simply growing installed capacity at assumed capacity factors in order to provide the terawatt hours. Okay. So the analysis then, this graph shows, if we look on the period from 2020 to 2050, how fast and how much the different technologies need to grow in installed megawatts or gigawatts in order to achieve net zero in electricity by 2050. And one point to note is we assume that electricity, in this case, is what we use electricity for today. So this does not include, for example, substantial electric vehicle usage. This is what we use it for today. Okay, and you can see here the coal is black, fades away to zero, gas fades away, hydro stays pretty constant. The green is wind, has to grow substantially. Dark yellow is utility solar. Light yellow is distributed solar. It grows until about 2035 when we think we might start running out of roofs. Okay, and the pink and the red are storage capacity megawatts. Now we know storage is not real megawatts, it's stored megawatts, but it gives you a feel for what the capacity is that we think we have to build in order to achieve this. And of course, the other thing with storage is we would have to build the wind and solar distributed around the country so you get weather distribution, right? You don't have the same weather impact everywhere at the same time. So that's the pretty graph on the left. So the right shows the rate of installation of technology that we would need. And what we've done is we've compared that with what we've been building in the last few years as a way to judge, is it difficult or is it easy? So distributed solar PV, we predict we need to grow about 2,000 megawatts per annum until 2035, when we think we run out of roofs. We've actually been doing more than that in the last few years, so that's okay. Utility solar, we think we need to install about 1,000 megawatts per annum. We've been installing about 800. So you would think that's also feasible. Wind, we think we need to install about 2,000 megawatts per annum. We've been doing a bit over 1,000, maybe possible too. Yeah? And one point to note is we assume a 2-to-1 ratio of wind to solar utility. It won't be that, it will be something else. That doesn't really matter for the analysis though, okay? And then storage, we assume distributed storage growth of around 500 megawatts per annum, and then utility storage around 330 megawatts per annum. Actually, in the last couple of years, we've been installing 2,000 megawatts per annum. So the storage has really gone through a boom at the moment. We think there will be a natural end to that, but that's showing what we can do when we drive around. Okay, so one conclusion you can draw from this is actually getting to net zero for an average day is probably within grasp for electricity, for the electricity industry. Yeah. And then we say, well, what do our graphs look like? So this is a prediction of what 2030 could look like. So we see we're growing wind, we've grown solar, coal does much less. And in an average day in 2030, we can see we're actually generating above the demand line. Why? Because that's where we're charging batteries. And then the batteries in the pink discharge in the evening peak by 2030. Yeah. So we can see we really are transitioning. Yeah. And then if we go to 2050, then it looks quite different. Okay. Now we have a higher demand curve. Why? Because population has increased. We're filling that curve with a lot of wind, pretty much the same hydro, utility solar and rooftop solar, and batteries discharging both in the morning and the evening. And we bring a new color in this purple, that's curtailment. So what we see is if we size our renewable generation to keep the lights on an average day, right, this is an average day, you would have no curtailment. But as soon as you have a below average day, then the lights start going out. So we have to oversize somewhat for an average day. Yeah. And that purple part is curtailment. Now, the purple part, it's really hard to judge how much curtailment we will have. It may even need to be quite a lot more than that. Yeah. That's something for the future to work out, because engineers and economists hate curtailment because then we're not using our investments. We think it's probably an essential part of a future energy grid, that there will be some form of curtailment. Okay. So that's our thought experiment. The next step we do is, what does net zero by 2050 look like? So what do we do? So we take all of the coal, all of the gas, all of the petrol, diesel, and aviation fuel out of the economy. Yeah. And we replace all of those fossil fuels wherever possible with direct electricity. Okay. And we generate all of that electricity either with hydro, wind, or solar. And where it's not possible to use electricity, the simplest example is aeroplanes. Currently, intercontinental jet aircraft won't be with batteries. Then you need some form of liquid fuel. That liquid fuel would be a chemical derivative of gaseous green hydrogen. Okay. So what do? So we electrify wherever possible. So that means houses are fully electric, industry wherever possible is electric. we stop importing petrol. So all passenger vehicles we think are probably electric. And if they're hydrogen, that doesn't make a huge difference anyway. We think electric vehicle arbitrage, where an electric vehicle is at home and plugged into a bidirectional charger, will be a really important part of the picture. It could reduce the required grid storage by 30%, which is enormous. Yeah. Otherwise, we use hydrogen everywhere else, either in its gaseous form or as in a liquid chemical derivative of the gaseous hydrogen. That means we stop importing diesel, aviation fuel, and other petrochemicals. And it means the hydrogen industry will be very large and becomes like today's oil and gas industry. We'll see how large in a minute. So the key design questions for us, if we were to do all that by 2050, is how much more electricity do we need for direct electricity and for producing green hydrogen? And then how much more wind, solar, and storage do you need to make all of that electricity? And what do you do about 3 to 5 days of bad weather? How do you handle all that? So they seem to be the key big design questions. Okay. So if we do the mathematics, we end up with this graph, which shows in the period from 2020 to 2050, the amount of electricity Australia as a nation would consume. So you see in 2020, 2025, we're at about 230 terawatt hours per annum. Okay. By 2050, we get to over 1,400 terawatt hours per annum. So we're now consuming 6 times as much electricity. Why are we doing that? Well, the light grey part in the graph shows consumption of electricity for what we use electricity for now. Okay. The greenish part, that shows where we would use electricity in place of fossil fuels that we use today. The purple part is where you have to make hydrogen to replace avgas, natural gas, fuel in long distance trucks, all those things. So there's a couple of conclusions here. So one is the hydrogen industry is now at 60% of electricity consumption, okay, bordering them. So suddenly in 2050, the largest consumer of electricity is the hydrogen industry. Yeah, that's a very big change. It's not industry and mums and dads anymore. The other thing that took us a little while to conclude from this, if this is what the future looks like, actually the answer to our 3 to 5 days of bad weather is in this graph. Because in order to make this much electricity, you have to have a very huge size of solar and wind generation distributed around the country. Okay. And that means, firstly, you get much better weather distribution connected with transmission, which is expensive. But if you have a bad situation, then you can treat your hydrogen industry as a disconnectable load, or disconnectable load. That means 3 to 5 days of bad weather. You have contracts with hydrogen that says, I'm going to turn you off when the weather is bad, and then I still have enough generation distributed around the nation to keep the lights on. And then I don't have to pay an enormous amount of money for storage, which I use for 3 to 5 days of the year. Okay. So that's a really important, we think is a really, really important conclusion. Okay. So then what does our installed capacity look like? And as I mentioned before, it's very, very large. So the same graph from 2020 to 2050, you can see the rate at which our different technologies have been growing until today, 2025. And then we see the rate at which they have to grow in order to get the whole of Australia to net zero by 2050. So if we look at the rates, right? So we assume distributed solar grows at the same rate and then we run out of roofs. Utility solar now needs to grow at 6,000 megawatts per annum. Okay. Wind at about 12,000 megawatts per annum. The electric vehicle arbitrage, we assume 28 million electric vehicles by 2050 with access to about 10% of the batteries at any point in time. Distributed storage grows about the same as before. Utility storage at about 1,600 megawatts per annum. That's been where we've been been today. So that seems possible, but still very, very fast for 25 years. Yeah, so we have to build this every year for 25 years. And we have to have the people, the concrete, the copper, the steel, everything. So this is very large. Now, you'd have to conclude that achieving this by 2050, given the rates we've been at now, is very challenging. Okay. And then what does the mix look like? So you can see on this graph, we're familiar with this graph now. The dotted black line was the demand curve in 2025. So now we see the demand line is much higher because we're making all of that hydrogen and because population has increased. And we fill that demand line with a mix of wind, rooftop solar, utility solar, and batteries discharging, and some curtailment. Yeah. So the thing with this energy system, we don't know how to manage this today. We actually have no idea how you would manage this right now. So this is complicated and requires all of the generation, all of the transmission, all of the hydrogen. So, okay. So we've been through that relatively quickly, a lot of very large numbers. Now I've got a few slides on what have we concluded, summarizing all those things and some conclusions. So the first question is, with all of the big numbers, everyone says, well, how big is big actually? Interesting question. So the solar, if we had to build 160 gigawatts of solar, that's about a 60 kilometer by 60 kilometer square if you built it all in one place, which you wouldn't, but if you did. Within Australia, that's actually okay. It's probably okay in Germany and France as well. Yeah? And then we asked ourselves the question, well, that's nice. We've got enough land. How much are we making today around the world? Can we actually buy this stuff? And the answer is for solar, probably yes. Right? So on most metrics, Australia is about 1% of the world. There's a rough rule. So currently the world production is about 21 gigawatts per week. We need 135 per week. So we'd be getting about 0.6% of world production. That might be okay. We still have to build 135 megawatts of solar every week for 25 years. That's very challenging. For wind, we would need to put about 43 wind turbines in the ground. We assume 5 megawatts per turbine. That's about 215 megawatts a week. There we'd be getting about 7% of world production. Right? So there we're sort of holding our hands up saying Australia is more important than other countries, which others might not agree with. And then batteries. So battery production has gone up really substantially in the last few years. Batteries, we're needing to build about 200 megawatt hours per week. Again, very challenging for 25 years. We're taking hold about 5% of the world's production. So let's say 5 times more than we deserve. Yeah. So big is big, is the answer to the question. So then some comments about society and economics. So in terms of the net zero challenge, we think net zero electricity is likely achievable by 2050. Net zero for everything is much more challenging, particularly in the time frame of 2050. We think there will be really significant supply chain issues for everybody. The investment in raw material, people, factory capacities, all those things will be very, very large. We think there's a role for regulation in all this, particularly around hydrogen. So we saw the RET in Australia, you would say, was one of the most effective government policies ever put in place. We think something like a RET for hydrogen placed in the right way may be a very good idea. And likely we need to have some form of carbon price. Now, the challenge with the carbon price is everyone knows it's probably the right way to go, but any country that does it immediately puts itself at an economic disadvantage to other countries. And the politicians who put it in place, they know one thing, that if they put a carbon price in place at the next election, they'll probably lose. So no country does it or has done it recently. So this regulatory thing is really important. We'll touch on it in the last slide. And then national economics, we think doing all this is probably in the range of 5% of GDP. for 25, 30 years. Yeah. We spend 2.5%-3% on defense. So it's a lot, but it's not unmanageable. And in Australia in particular, those costs will be defrayed because we're no longer importing petroleum. And we import basically all of our petroleum. And it's a lot of money. Yeah. So there's some interesting conclusions there. From a technology perspective, okay, we know we have to build a lot of renewable generation. Some form of base load renewable would be great. Unfortunately, geothermal's technology has not really improved much in the last decade. If it does, that would be an interesting candidate. We know energy storage will be really critical. So geographic distribution of the solar and wind makes a big difference. We think this using hydrogen as an effective storage of energy will be very relevant, both as a disconnectable load, but also potentially as stored gas that can be burned in gas turbines. And the electric vehicle arbitrage thing, we think is a really important concept for effective storage that's nearly for free because people buy electric cars anyway. Hydrogen production, we see that we use actually more electricity used for hydrogen than for electricity. It's a really important conclusion, we think. And then the chemical derivatives of green hydrogen being used for things like aeroplanes and long distance load haulage, we think will be really important. And then the impact on transmission. We need a lot more transmission. If we generate 6 times as many terawatt hours per year, it's difficult to judge how much more transmission we need. Is it 6? Maybe not. It's probably at least 4. That's a lot of transmission. Yeah. We think there's a case for an east-west link across the Nullarbor. And certainly residential virtual power plants. So storage in houses will be an important part of the picture. And then a question for the green hydrogen that is discussed a lot or has been is, let's have Australia become a green hydrogen export superpower, right? We see it in the media quite a lot. It's an interesting question. So in order to try and analyze that, what we did, we said, well, so far in this presentation, we've talked about Australia's domestic energy demand, but no export. So, well, how much do we currently export as natural gas and coal? And the answer is about 14,000 petajoules per annum. Now, that's a difficult number to quantify. So if you look at the pie chart on the right, the colourful part, that's our energy consumption domestically. Yeah? So if we were to export as much in the future, in 2050, as we do today as coal and natural gas, but export as green hydrogen, we'd have to produce the part on the left. So it's basically double again what we produce domestically. Yeah? So all of those numbers, the pretty graphs we looked at that show how much solar and wind we have to make or build in order to provide our domestic energy consumption, we have to double all of that again if we are to stay as an energy exporter in the same magnitude as we are today and replace all of the coal and natural gas with green hydrogen. Yeah. So for me, a real question is, how do you do that when it seems that just providing our domestic energy requirements will be such a challenge? Okay. I guess from all of that, some guidance for a plan for the near term and some conclusions. So what we think we need is a plan to achieve net zero that is flexible and can be adapted as we move along, because things change. We know that things will change. So green hydrogen, I think we've seen, other than if we wanted to build large-scale nuclear, which seems to be off the table, green hydrogen seems to be a really big part of our energy future if we are to get to net zero over whatever time frame. Yeah? And the economics is the key. The current small-scale projects work only with pretty significant subsidies. We think that's not the way to start an industry. Maybe a focus on diesel replacement and chemical usage is important in the short term. And export at $6 to $8 a kilogram, you have to wonder whether that works. And we think we need some sort of regulatory target. Blue hydrogen is a natural competitor for green hydrogen. But once you factor in the carbon capture storage part, it also becomes expensive. And the question is, can it be made to work economically at scale? And on natural gas, if our coal generation shuts as planned, there's a real question that says, will we have built enough renewables to replace that coal generation? Currently, the answer is probably no. And then you have a significant role for natural gas in the transition from now until 2050 or 2070 or 2100. I think transmission we've talked about, the existing renewable energy zone ideas we think are working quite well, but we need to build a grid that can do 1400 terawatt hours per annum. And then the point in the bottom corner, this is, we think, really important, right? How do we as a country manage this tension between the need to build large-scale wind, solar, and transmission projects with preserving the environment, preserving heritage, and social equity? I mean, we've been trying to build literally a handful of transmission lines in this country in the last, I'll call it half a decade, not very successfully, because people don't like transmission lines in their backyards. That's sort of understandable, but how do we find a balance between those things? I think as a nation, we're not doing a very good job of that at the moment. Okay, so last slide. So from some conclusions, is all of this actually possible? Well, it's hard to answer. Certainly in a 2050 timeframe, very challenging. Yeah. We have a clear goal, which is to get to net zero as a nation, and for every nation, we need a plan on how to get there. And green hydrogen, we think, has to play a really significant part, but the economics are very challenging. And we have to start now if we're to have any chance of getting to something like net zero by 2050. Now, you saw we've actually done a pretty good job in the last decade, even 15 years. The question is where to from here and how fast? And a really fundamental question is, how do you economically transition to an energy system with significant green hydrogen when currently the economics of green hydrogen are so difficult? And it does seem that energy in a renewable world will become more expensive, not cheaper. Yeah. And the communication to society around that really does need to be transparent. Otherwise, there's a real risk that society says, you know what, we like our cheap fossil fuel energy. Yeah. And that would be a real shame. And all of this requires strong national and international alignment. Now, you think about when the Paris Accords were signed, it looked like we were getting strong international alignment. You could observe that that's fallen down somewhat in the years since. Yeah. So there's a lot of challenges ahead of us. So thank you for your time, Franco. If I go to Q&A slide.
Okay, great.
All right, thank you, Michael, for a very interesting talk and for providing lots of food for thought, I think. So maybe we start with questions from the audience here.
Hi.
Just we're online.
I'm sure you can hear me without this. Do you have a copy of?
No, our online audience
Oh,
won't be able to
oh.
hear.
I apologize. Richard saying. There seems to be an exponential growth due to population growth. I'm wondering if you more gained, not the extreme, but a fraction of that extreme, to see if there's a natural population growth target or a population growth target that might ease off on that exponent so that we don't need to use so much electricity to generate more hydrogen. There's a power equation there, isn't it? Because we're actually going away from with electrifying, and we're also generating gas using electricity. And population growth is driving some of that. I'm excluding, of course, exports. So if I just ask that question, have you all gained a fraction of that population growth? Thank you.
We haven't. I think we've taken the population growth numbers that the government expects. And currently, that they seem to be reasonable numbers. We also made some assumptions about increasing or improving energy efficiency. So we haven't done a linear model on how much each person uses. We've decreased it somewhat. Yeah, but we certainly haven't done the wargaming thing of saying, well, if we reduce that or even reduce the population in Australia, what does that look like? The population growth thing, of course, is quite a sensitive topic politically. So we've basically done that as an assumption into our model. And you can imagine doing this sort of modeling, you have to make a very large number of assumptions. And one of the things we tried to do in all this was to say that in a room like this of people who know about energy, that we could look at each of the assumptions we made, and everyone in the room would say, you know what, that's a pretty reasonable assumption to make. So our reasonable assumption on population is use the government's projections. We haven't done any scenario modeling on what happens if it gets higher.
Hi, thanks, Michael. That was very good. Cormac is my name. I'm an energy consultant. And I might ask for forgiveness for asking 2 questions. First, having spent about a year designing the hydrogen derivative fuel plants, I was a bit shocked how inefficient they are. So when you're massive 30%, so 60% of future generation going to hydrogen, I was wondering what your assumptions were for the efficiency of those hydrogen derivative fuel production, because it can be very low from what I
You mean the
know,
conversion of electricity to hydrogen?
to the end hydrogen derivative fuel, if you need to make like an F-gas out of green hydrogen.
Try and answer that question. So it's essentially what we assumed, if you take an aeroplane, for example, we assumed efficiency similar to today, and then calculated how much hydrogen would we have to produce in order to make enough liquid fuels to replace the fossil fuels we use today.
Correct. So, I mean, the poor figure I have in mind is about 10%. So if you start with 100% renewable energy, you're only going to end up with 10% of that as a fuel.
Sure.
But then you lose the combustion another half. Right?
Well, and all those technologies, they're technologies we use today. So I think an interesting example that I like to use to demonstrate exactly that point is if you were to make 100 megawatt solar farm with let's call it a 30% capacity factor, and you used all of that electricity to make green hydrogen, you stored that hydrogen, and then you used it to drive a baseload combined cycle plant, a gas turbine combined cycle plant, with a 60% efficiency. So let's say today's best case today, you would get 12 megawatts baseload out of that plant.
I meant the green fuel derivative. So you refer to a lot of that hydrogen going to create green fuel or hydrogen derivatives.
Yeah.
So effectively creating a fully green methane or a fully green hydrocarbon that can be burned as
methanol or derivatives from methanol, those sorts of things.
So that's the 10% that I was referring to.
Yeah.
That's the core figure I had.
I
I'm wondering what Siemens has assumed for those types of green.
I can't remember. I don't think we've done a one-off assumption like that. What we've done is looked at each of the usages for the energy, and then looked at what is current technology, and I don't think we even improved them very much. Yeah, but you're right, the conversion in the, I mean, it's interesting. You have to sort of almost invert your thinking in when we talk about renewable energy compared to fossil fuels, because of course fossil fuels, the money is in the fuel you burn, and the capex, while as part of the equation, is often the smaller part, whereas in renewables the money's in the capex and the fuel is for free.
This is where I beg forgiveness. You also mentioned, my second question, you also mentioned carbon capture and storage. What are your thoughts on that? It seems to me there's a lot of juries that are a lot out on this. I've heard people say it will never work, this stuff underground somewhere, it'll just leak out again. So what are your thoughts on that?
I'm not a geologist. So I guess we have to believe the geologists when they say we think it won't, and then some geologists think it will. I can't judge. Where I struggle is it seems like a short-term solution, because if you say we have to get to net zero, we have to get something like we've looked at here today, either this or nuclear, or someone comes up with some technology we don't know about today. And at some point the natural gas runs out anyway. So maybe someone says we want to do carbon capture storage as part of the transition, great. But it's still expensive. And as you say, there's the risk of leakage, who knows? So yeah, for me, it's not a technology that you do forever. Whereas this sort of picture says, actually, if we can get to the picture we've got, probably not by 2050, that's almost a forever picture. Yeah. At least until the sun stops shining.
Your assumption seemed to be that you're achieving hydrogen at about $6 to $8 a kilogram, rather than the $2 a kilogram that we used to talk about. At $6 to $8 a kilogram and at say 50% efficiency, open cycle gas turbine, what sort of power cost are you talking about for peaking power? And how does that compare with solar now at about $50 a megawatt hour?
So a couple of points. First point, we didn't assume $6 to $8 a kilogram. We said currently with small projects, that's probably what it costs. Yeah. The other thing that maybe doesn't come out too strongly in this is we don't think in the very near future burning hydrogen for power generation is the thing you'll do first. It's something you may do towards the back end of this when you have a big hydrogen industry and you've got, for example, excess hydrogen and the sun's not shining. So a short-term focus on does hydrogen in power generation make economic sense, I would actually say is the wrong question.
I was just thinking that last night, for instance, about 6 or 7 o'clock, peaking power spot prices were about $600 to $700 a megawatt hour, based largely on gas, I guess, or being driven by gas. I was wondering what the $6 to $8.
Off the top of my head, I couldn't tell you. It's not an example I have, but it would be very expensive, probably of that order or maybe higher.
I think it'd be a lot higher than that, but I don't have it on the top of my head either.
No, but very expensive. So as I said, the using hydrogen for power generation is one of the later things you do. You use hydrogen first for chemical replacement, for diesel replacement, for avgas replacement as a sequence of things you'd likely do. Power generation probably comes later in the piece.
I appreciate that. What concerns me is this time of the year. Okay, July, August, it's a sunny day today, but quite often we have little wind. So there's 6 or 8 weeks, often at this time of year, when there is little capacity for adequate renewable generation. And if you're going to store up energy for that length of time, well, it's not practical with batteries, and there's no hydro, but you might need half a dozen of them. So if you have to go back to something like hydrogen, costs become enormous.
And that's where, it's an excellent question, right? And then what are your options? So a couple of different options. So one is you have a very distributed, a geographically distributed installation of wind and solar and a good transmission system. And then even though in Melbourne, today is nice, it's sunny, but let's say on a typical Melbourne winter's day, it's a bit overcast and not very windy, then you're probably going to be importing power from Western Australia or Queensland or somewhere else. But then you have to have a very, very large transmission system, or gas pipelines with hydrogen. It's also a question, but then it comes back to the economics of what does all that look like. But I agree with you. You're trying to do battery storage in Victoria for 7 days, and you're trying to pay for the batteries just in those 7 days. Very, very hard economic.
Mustafa from Melbourne. One of your forecasts, when you were looking at forecasting the amount of electricity that's needed to replace for hydrogen to replace fossil fuels. Okay, I think you showed that wind turbines need to ramp up to 12,000, so almost 12 times of annually from now until 2050, right? But then there's a lot of capital investment that goes in all this ramping up. So and hopefully that somehow will be offset with exports if exports are to be part of the equation. But then you said that exports, the requirement will be almost double. Like in terms of total amounts that electricity that you need to be able to export. So then instead of 12,000, you might need 24,000
Extra,
extra.
so 36,000.
So 36,000 for 25 years. Do we even have the land, like the land area with appropriate conditions that can fit as much wind turbines?
So I think in Australia, the answer is probably yes. An interesting question is if you pose the same set of questions for every other developed nation, do they have it? And then the answer is probably no. Yeah. So in Australia, the land area is probably the least of our problems. It's more about approvals, the people you need to do it, the concrete, the steel, the copper, the everything else. Yeah. Land, probably not the issue, provided you can get approval to build your wind turbines on land where the wind blows.
So what land where wind blows, there is actually enough for
So to be clear, we haven't done a study to validate that. I would say from just the size of the continent perspective, you'd have to say probably yes.
I'm Michael, technical engineer. I wanted to know a bit more about introducing hydrogen into natural gas pipelines. You mentioned about that. Is that as simple as, the 10% ethanol in fuel, and we still go about our ways without, a lot of infrastructure investment? So 10% hydrogen in natural gas pipelines should still work with the polyethylene high pressure gas pipelines we have in place already.
Yeah, I think the main issue I'm aware of with injection of hydrogen into the existing natural gas network is about the hydrogen embrittlement of the pipelines, and something up to 5%. There's somewhere there's a borderline. Unfortunately, I'm not a metallurgist to tell you what that is, but let's say 5-10% is people have been doing trials. There's a trial been going for a few years in Adelaide where they're doing exactly that. It's injecting, I think, up to 5% hydrogen, green hydrogen, into the suburban gas network in Adelaide. So that can work, and I think most devices that consume natural gas can cope with 5 or 10% hydrogen in the natural gas. Works okay. Sure, yeah. And it's one way. It becomes a little bit like the red we had for wind and solar, right? For electricity, if you mandate that the gas suppliers have to have, let's say, 5% green hydrogen in the natural gas, then we all pay for that. It's only a small amount, but you actually can start a hydrogen industry by doing that. Could be one way to start the industry.
Take one more from the audience here, and there's plenty of online questions.
This is Patrick Quinn from Plant Bioenergy. So this is more a comment, but it is interesting. There was I don't know if you saw it last week. There's a report from Bioenergy Australia and Deloitte and Bloom and various other things, essentially saying that we could replace upwards of 95% of domestic gas consumption with bioenergy, biomethane, essentially. What's fascinating about the charts you said there is that that's a relatively thin slice of, so even if we do get that path and essentially the methane number doesn't fall to zero, it still leaves this massive gap of additional energy that needs to be built for everything else. So yeah, I was wondering why that wasn't sort of mentioned when I was thinking out of something, because you're solving a different problem.
So I think I'd have two comments. So one is, we're very certain that the future doesn't look as simple as my graphs, right? They're there to get as I said, a rough feel for the size of the numbers and the speed. And I'm sure there will be lots and lots of energy technologies and smallish industries that are built because they make sense, like biomethane. So that's one point. The other point is, though, that's exactly an example of when I started, of you've got media and silo groups making announcements to the, let's face it, not very well informed general public that distort their views because they're made without the context of the overall picture. So that's what we've tried to do here, is have a look at green hydrogen in the context of the overall picture, because without the overall picture, you don't know what you're talking about.
Thank you.
Actually, that last comment addresses a lot of the questions that we had online, which were about, why not use bioenergy for the things that you can't easily electrify? So I guess that, a lot of the consumption, what you talked about, which is a lot more actually than the electricity, but we need more electricity to decarbonize things that are not electrified. So can we use biomass or bioenergy for that?
Absolutely, but when you look at it's all about energy density at the end of the day, and all the bioenergies we've seen have very, very low energy densities. If you look at, well, how many hectares of land do you need to grow sugarcane, all those things, they end up being, I'll use the term niche technologies. They're partial answers to this big picture. We haven't seen anything that would say, oh, we don't have to build wind because we can do a bio XYZ technology. It's not the nature of the thing. Yeah.
Another question online was, have you kind of only considered batteries when you talk about storage, or are you talking about all kind of other storage technologies, including pumped hydro?
So in here, we've got graphs that say batteries. Actually, it doesn't matter what the technology is underlying. It just says you have to build X megawatt hours of storage in order to back up the wind and solar that you're building to provide energy for society. Maybe your comments are for hydro in Australia, it's the driest continent. I'm not aware of too many large-scale opportunities for pump storage hydro that remain. There might be 100 megawatts here or 200 megawatts there. Yes, they're good things. They become part of that mosaic of answers to these questions. Are they the big answer? No, I don't think so. It's like ocean power. Australia is a huge continent, lots of coastline. You think, why don't we use ocean power? The energy density is very low. You need very specific geographic locations, and it's because of all those things, it's very expensive.
Can I get a comment from the audience?
I think your mention of water usage maybe has been a little bit under.
So
Your mention of water usage has been a bit under asked, because obviously we are the driest continent and electrolyzers use truckloads of fresh water to create hydrogen. So my question was going to be: is Siemens developing, or have they developed salt water electrolyzer to avoid?
So again, I like the questions that have been fantastic. I like them because they lead me into discussions. So I'm not aware that we have a salt water electrolyzer. Certainly one of the discussions in the industry is, if you're making so much hydrogen and you need a lot of water and you don't have the fresh water available where you want to make hydrogen, do you have a renewably powered desalination plant which produces water for your electrolyzer, which produces green hydrogen? You can do all that. It's just expensive. One comment, the rough numbers we did in Australia to provide our domestic demand for hydrogen, according to this analysis, you would need to consume about 10% of our domestic water consumption. Okay, now and we use a lot more water for industry than we use domestically. So we think that 10% of domestic water consumption, that's actually not too bad. Now you have to be careful about where you place the electrolyzer plants in order that you're not locally consuming too much fresh water. But from an overall perspective, we think actually it's okay. Then when you start to move to double that again to do the export, and then you're talking about 30% of domestic water consumption, you start to get quite a lot of fresh water, and maybe you have to talk about desalination. But actually, for at least for our domestic requirements, about 10% of domestic water use.
Hey, I think we're kind of out of time already. It's obviously generated lots of questions, and I apologize that we couldn't answer them all, especially there's quite a few unanswered online questions. But yeah, please join me in thanking Michael for his involvement.